nuclear reactions studied with the Trojan horse method.
Thank you. Thank you, Mr. Chairman. Good morning. Let me first say a few words. I want really warmly thank the organizers for taking me here. It's really a pleasure to be part of this community, to see a lot of new young people. Okay, so I think my talk is a bit different from the ones we saw yesterday. I'm not going to speak about multi-neutron transfer, but I will speak about transfer. Maybe multi-nucleon transfer, so protons and neutrons together. Let's see. So, yeah, the title is the one you can read, and this is a short outline. I'll try to just to make an introduction to explain the need of indirect techniques in nuclear astrophysics. I'm sure you know the story, but since there are some students, it might be useful, and then I will move to. You hear me perfectly, right? Okay, because I hear some noise. So I move to describe the Trojan horse method, and then I will focus on physics, a few physics cases. So this is something quite clear, that when we try to measure reactions between charged particles at astrophysical energies, of course we end up in a huge difficulty, which is connected to the extremely low cross-section, which can be also of the order of picobarn, or even reach the femtobarn range. And this is essentially due to the Coulomb barrier that is responsible indeed for this very low signal-to-noise ratio. And so really people, they try to get to the astrophysical region with a lot of troubles. Just consider that astrophysical region for the inner part of our sun means energies of the order of tens of keV, while the Coulomb barrier between two protons is around 500 keV. So there is kind of orders of magnitude the difference, so the cross-section really drops. And so how to get some information of astrophysical relevance? Either we try really to go down with the energies and to afford these challenging measurements, or at some point we give up and try to extrapolate it in the astrophysical region, and usually the extrapolation is done, maybe you have heard about the S factor, using this conventional factor, where essentially you remove the bulk of the Coulomb suppression by multiplying the cross-section by this exponential factor that is the inverse of the gamma factor. However, the extrapolation, can be dangerous, because usually you go into a region where you are not sure that you know everything in terms also of nuclear parameters. And really, in order to, let's say, to avoid extrapolation, people went also to run experiments underground in order to, since we cannot improve the signal, we try to reduce the background, to reduce the noise. And I like to show this figure because it's amazing that, so Luna is a collaboration working in Italy. in one of the 4 national laboratories that is called Gran Sasso Laboratories, really inside the mountain. And they had this phase 1 lasting for 9 years, and in 9 years they have been able to measure only 2 reactions. This was amazing, just 2 reactions in 9 years. And the situation here is really, you see, is really challenging. So for the helium-3 plus helium-3 going into 2p helium-4, they measured 1 count per month. This was an extremely important experiment. They were looking for a resonance here that, in order to justify the loss in the neutrino flux, in the solar neutrino flux, but they didn't find any resonance. And we know that in the end, the problem of the neutrino flux was solved with the neutrino oscillations, but they tried also the nuclear physics solution. But they found something which was not known at that time. These, I would say, artificial increase of the S factor and thus of the cross-section at low energy. I must say artificial because this comes from the electron screening in the laboratories. Now we know that electron screening is also important in stars, but of course in laboratories reactions behave in a different manner because you have a target and you have a beam. And usually these 2 objects, they are not fully stripped. So after those measurements, after this important phase 1 of the LUNA collaboration, we discovered this intrinsic limitation of direct measurements at astrophysical energies, that is electron screening. And essentially, yeah, electron screening is due to the electrons surrounding the interacting ions. And the effect is indeed to screen the Coulomb potential. And let's say the macroscopic effect is this increase in the S factor. And this happens at energies which start to become comparable with a screening potential, or let's say 1 order of magnitude larger than the screening potential. So you start seeing these screening. And after that, really, people, they have been really very much engaged in order to understand this kind of behavior. And apparently, so there is no solution. What people understood that perhaps this increase is not only screening, or it's like 80% screening, and partially is due also to the dynamics of nuclear reactions at low energy, because it's like since you have 2 interacting nuclei below the barrier, somehow they put in a way, so it's a very classical picture, somehow they try to reduce the Coulomb barrier in order to fuse, and we should account also for these dynamics. And why this kind of idea? Because indeed there is no, let's say, the atomic physics model allows us to determine what is called the adiabatic limit. That should be the upper limit for the screening potential. And from laboratory experiments, we get screening potentials that are larger than these upper limits. So something is missing. Well, so that means that we don't have, let's say, a model that we can trust in order to remove this screening from laboratory experiments in order to assess the reaction rates correctly, because then we have to put the screening in plasma in order to get the correct numbers. So at that point, people, they understood somehow that in order to get what we call bare nucleus S factor, so the S factor without the screening effects, the only way is to extrapolate from the higher energies. So it's like any measurement in the region where screening becomes important is useless, something like that. Not exactly like that, but this is kind of extreme consideration. So that's why really people, they started also to think about other techniques, and indirect methods were introduced in this field. And essentially, you know, indirect methods, they allow to measure cross sections at never reached energies. So really to go down into this, let's say, challenging region. They also allow to get independent information on the screening potential. And nowadays, we can say that they also allow to overcome difficulties in producing the beam or the target when radioactive ions and neutrons are considered. So, and I must say that also the experiments, they look much more straightforward than the direct measurements. And you have a way to overcome the Coulomb suppression and also the electron screening. Of course, you have issues coming. And yeah, the main, let's say, something you have to really to consider, that essentially you are not measuring the right reaction you need, and so you have to get it from another reaction. So indeed we say that the entrance channel that you measure and the reaction products, they can be linked by several reaction mechanisms, and so you have to go to select the proper one, and to do that you need a reaction theory. However, so after, I must say, how many years? 3 decades, 30 years, we did, I mean, a lot of work, and I'm not in the field, I've not been in the field for 30 years, but it's already quite a lot, and I mean, we developed also very nice techniques and observables to make a careful data analysis. And I will just go straight on this Trojan horse method, but of course there are others. And yeah, maybe we can discuss later. So this original name, the Trojan horse method, was invented by Gerald Bauer in the late 80s. The idea is very original. Then somehow we had to, let's say, to slightly modify it in order to make it compatible with experiments. And the idea is the following. You want to measure the cross-section of a given two-body reaction, and in order to do that, you run an experiment with a 2 to 3 body reaction, which should be a kind of appropriate one. That means that either the projectile or the target, so here we call it a small a, this is a small a nucleus, that can be either the projectile or the target, is clusterized in terms of these two nuclei, X and S, or particles, where you see X is exactly the participant of the two-body reaction of interest. And so the trick is that so the interaction energy, you use an interaction energy between these two particles, which is above the Coulomb barrier in the entrance channel. And so it's like you're using this small a nucleus, which is our Trojan horse, in order to bring X already in the nuclear field of capital A. So you're just making this X nucleus able to overcome the repulsion wall. So something which is very old. It was very powerful and successful because Troy was destroyed thanks to this nice idea. And I must say that we did also a lot of nice work using it. And yeah, essentially from the, let's say, experimental point of view, you got to really to select a region in the phase space where this quasi-free kinematics is really governing the reaction. And essentially it's, you have to have these, you have to consider that only this X particle will interact with capital A, leaving the other as a spectator. So a spectator means essentially that S will fly away with the same momentum it had inside the Trojan horse nucleus, inside the small a. If we want to use a diagram with this pole diagram to describe, to sketch what's going on, we have these two vertices. In the first vertex, small a breaks up into its components, and then X is transferred to the second vertex where the two-body reaction takes place. And here comes another trick. So the other trick is that what you are transferring is a virtual particle. You will never see it. And this means that the entrance channel here is off the energy shell. So you cannot write that E is equal to P squared over 2m. But it's like you have to put an additional energy, an additional fee you have to pay in order to make these two objects to break up. So you have to destroy the binding of small a. So you have to pay a fee which is exactly the binding energy of these two particles. So you have to inject a lot of energy. And this is the trick, because this makes you really running the experiment at quite high energy. So you don't feel any Coulomb suppression. And you need it, you need this binding energy in order to compensate for the beam energy. And so, thanks to this relation that comes from energy conservation principle, you get what we call quasi-free energy. This is exactly the interaction energy between these two objects, which can be as low as you want. Can be also zero, it can be negative. So you can be able, with this technique, also to populate states below the threshold. So really to study bound states. Because what you are measuring is the exit channel. This is on shell, of course, okay? And then you see here, you have the intercluster motion between these two objects that you can use to span the astrophysical region of interest. So in the first part, you get just one energy. So with a given beam energy, you get just one quasi-free energy. But then with the intercluster motion, you can span, let's say, few MeV, in order really to populate all the astrophysical region of interest. So with one experiment at a given beam energy, you can populate all the astrophysical region of interest. This is also, I mean, very important to say. So we did many measurements. I will tell you later. Just a few words on the theoretical approach, because so in order to make life, let's say, relatively easy, and since we are running an experiment, so we are able also to cut a portion of events that makes life easy. We usually try to end up in what we call this plane wave impulse factorization of the three-body cross-section that we are measuring in terms of, you see, a kinematical factor. this quantity, which has inside the momentum distribution of the spectator inside A, that in plane wave is just a Fourier transform of the radial wave function describe the intercluster motion between X and S, and what you need. What you need is the nuclear cross-section for the two-body reaction of interest. But this is just the nuclear part. And so then if you want to make a comparison with direct measurements, with direct data, you have to, let's say, to reintroduce the Coulomb suppression. So, however, if you stay with this factorization, you get and of course you have to make an important selection of data and so on and so forth, you get the energy dependence of the two-body cross-section, but not the absolute value of the cross-section. So in this sense, you need direct data at higher energy in order to normalize your trend. Yeah, just to show you that we have also a more, let's say, complex formalism that has been developed for resonant reactions, but still here in these parts of the formula which are highlighted, you can recognize the factorization. Okay, this is the transfer amplitude, and this is the momentum distribution, and this is connected with a two-body reaction cross-section. Yeah, just to say a few words on resonant reactions, because as I will show you in a minute, we have done a lot of work for, let's say, reactions where you have resonances, because if you move a bit far with nucleosynthesis in stars, and so you start working with heavier systems like we did for, let's say, carbon plus carbon, carbon plus oxygen, but also other system, heavier plus lighter, you end up with resonances. And in order to account for this resonant behavior of your reaction, theory has been developed by Akram Mukamedzanov in order also to account for the off-shell nature of this two-body channel, of the entrance channel. So for resonant reactions, you can indeed consider what it is sketched here as a transfer. So this is really a transfer to the continuum, because you are populating a state which is above the threshold, and then it decays, and you can observe its decay. And usually resonances are treated with R matrix, but you cannot apply the R matrix in this case because of this off-shelliness nature. And so a modified R matrix was introduced. Essentially, so this is the way we parameterize the two-body cross-section when it is resonant. And you can recognize a kind of a bright Wigner, where the gamma in the entrance channel has been replaced by the square of the transfer amplitude. Okay, this is somehow the trick, something that you can easily calculate. And essentially the other thing I want to you to notice that if you make a transfer to a bound state of this compound, m square, this term, will be proportional to the A and C, and in this case you can see the connection between the Trojan horse method and another indirect method that is called asymptotic normalization coefficient method that works for bound states. And yeah, essentially what you do is just you get this two-body cross-section from experiments. you run this modified R matrix, you determine your resonant parameters, and you use these resonant parameters to determine the on energy shell S factor, something that you can easily compare with direct measurements. So here, just a list of reactions that we have studied so far. I must say that almost, let's say, the bulk of the work was done by the Catania people. So this is something that, let's say, the international community somehow is complaining, in the sense that only we are running such a kind of experiments, and we have, let's say, codes in order to analyze data. But I must say that there is a community in China, in Beijing, that is working independently. And so we are very happy for that. So you see, we really span several, let's say, so usually the motivation is connected with nuclear astrophysics. So we measured some reactions which are in the so-called network of reactions which are relevant for the Big Bang nucleosynthesis. And you can recognize, for example, the lithium 7 plus proton, the lithium 6 plus proton. There are also these reactions that destroy beryllium and boron isotopes, which somehow are connected also with the Big Bang nucleosynthesis, but not only. And you have also the DD reactions, these two fusion channels. And then we did also work in the framework of AGB star chemical evolutions. Yeah, we studied the fluorine 19 nucleosynthesis path. And as you can see here, we did also a lot of work for this carbon-carbon fusion, which is the driving reaction for carbon burning. The carbon burning, I think it's the next, yes. So the carbon burning is the third most important phase in the, let's say, hydrostatic burning of a massive star. So a massive star starts with hydrogen burning, then it moves to helium burning, and then it goes to carbon burning. And so only 5 minutes, so I have to run. Okay. Yeah, and I mean, it's very interesting. So I really started my, let's say, academic career where I was doing my master thesis with carbon plus carbon. At that time was very, let's say, famous to investigate clustering structure in magnesium-24. There was the so-called 6-alpha chain around, let's say, 30 MeV of excitation energy. And so really I was somehow fed up of all this story around carbon plus carbon, around magnesium-24, but I didn't expect that at that time that indeed the region of magnesium-24 above the carbon-carbon threshold, which is about 14 MeV. So the carbon-carbon threshold is at 14 MeV of excitation energy. So the region between 14 MeV and 16 MeV is extremely, extremely important for nuclear astrophysics. And yeah, it was really very nice. And apparently, this is also the region for collective for giant resonances. So at 15 MeV, you have the giant dipole and quadruple resonances. So apparently, it was quite well studied, but as it happens quite often, the communities, they don't discuss. So nuclear astrophysics was looking for resonances, but a lot of work was already done. So what we did, so you see here at that time when we decided to investigate the carbon-carbon interaction by means of the Trojan horse method, we went looking at the data, the direct data, that they stop around 2.2 MeV. So 2.2 MeV means above 16 MeV of excitation energy. So just at the beginning of the astrophysical region of interest. And going below directly, it's so challenging. It was really extremely challenging at that time. That means some time ago. Now people are becoming, let's say, that they measured and they did a lot of experiments. They will try really to get into this, let's say, difficult region. But anyway, we tried, and it was already some time ago. In 2018, we published this nice paper where we started from nitrogen-14 as Trojan horse nucleus. So indeed, the idea, let's say we took the idea from the Russian colleagues that they studied, that they did nitrogen-14 plus carbon-12, and they observed the transfer of 12 nucleons from nitrogen-14, so carbon-12. So we did exactly what they did, what they have done, with different purposes, and running a Trojan horse experiment. That means that you go to select a proper region where you can extract this two-body reaction. And so, yeah, there are some, let's say, details of the experiments which was quite standard. Maybe you can ask. And we discovered a lot of resonances. All these resonances that completely change the idea about let's say the trend of the S factor. At that time, people they were considering a non-resonant S factor. Now we know that resonances, they can dramatically change our belief. Okay, I'm not going, so this triggered a lot of studies, a lot of debate. I'm not going into the details, so you can ask. And yeah, we got a huge increase in the reaction rate, which is compatible with some astrophysical observations. And in particular, the story of the superbursts, these long-lasting X-ray emissions from the surface of neutron stars that are accreting material from a companion. But this was just a part of the story. We could also set what we call M-up. M-up is a threshold in mass for these massive stars in order to trigger the carbon burning, and other things also connected with core collapses, supernovae. And okay, we are continuing also with carbon plus oxygen. We have very nice results, and the paper is in preparation. Again, here, the problem is that data, they stop around here, and we measure it down to 2 MeV. Same story. And maybe if I have just a couple of minutes, I would like to mention another, let's say, nice, I must say, like a present, you know, you're running something with other purposes, and finally you end up in something unexpected. You have an idea. And indeed, we could, let's say, go deeply in the so-called charge symmetry of the NN interaction. Essentially, you know, the charge symmetry means equality between the proton-proton and the neutron-neutron force. And the charge symmetry breaking is mainly due to the difference in mass between up and down quarks. And a way to, indeed, to get into the charge symmetry breaking is to measure the scattering lengths. So the NN, NP, and PP scattering lengths. However, so while NP can be determined from experiments directly, the proton-proton scattering length is something that you cannot measure. So you can measure directly, but you have the Coulomb interaction that makes things complicated. So you determine the scattering length with the Coulomb interaction, and so you have to remove it. So just to give you numbers, the scattering length, the proton-proton scattering length with the Coulomb interaction is minus 7.8 Fermi. When you remove these Coulomb effects, you get something like minus 17.6. So the numbers are really different. So the Coulomb interaction really plays an important role. And of course, ANN is not directly accessible from experiments because you don't have neutron targets. So what we did, in former times, that means almost, yeah, I must say 18 years ago, we made an experiment in order to test really the method, the methodology, in order to better understand the suppression of the Coulomb effects. And we measured the proton-proton elastic scattering by doing the PD-PPN quasi-free reaction. And I mean, it was really a surprising result because here you can see the two-body cross-section. So this is the scattering, the PP scattering cross-section. You can recognize the minimum. The minimum is a signature of interference between the nuclear and the Coulomb force, yeah. And what we got instead was this trend, so no minimum at all. And we interpreted the absence of the minimum as a suppression of the Coulomb interactions. So at some point, some years ago, we just thought, why don't we use this trend in order to get an estimate of the scattering length for the proton-proton without the Coulomb effects, so a Coulomb-free scattering length. And this is what we did. So I go very fast. Essentially, this means to do a fit with a conventional tool to analyze the nucleon-nucleon scattering. And we did a Bayesian fit, and we got this number, minus 18.17, which is the scattering length, the proton-proton scattering length, Coulomb-free. But we understood also something which, at least for us, was not clear. This is what we call the short range, so the scattering length coming from short-range physics. That means that it has inside also the electromagnetic part, the short range of the electromagnetic part, which usually is removed. And so with this trick, we were able to really to assess the charge symmetry breaking, or to say something about the charge symmetry breaking of the short-range interaction as a whole, because this is also what you can determine for the neutron-neutron scattering length. Okay, since my time is over, anyway, we got the assistance of Alejandro Kiewski and this group from Pisa in order to assess really these numbers, let's say theoretically trying to understand in terms of universality what this means, and they could develop a very simple model. They could construct a very simple model in order to, let's say, to describe the interaction potential of these two protons and play in order to, let's say, turn on, turn off the Coulomb interaction. And if you are in this universality window, and this is the case once the Coulomb effects are removed, essentially your potential, so what you get, the interaction is not sensitive to the potential you are using. And surprisingly, they got numbers which are very much close to those. Yeah, we got. Okay, I can stop here. I leave you with this nice figure, and thank you so much, and sorry.
So thank you for this nice overview. I mean, we're done with the discussion time, but I think we can go a little bit into the time for the
Maybe
next talk, if there are any questions.
Or we discuss later.
Nia?
the reaction in the presence of a resonance. I thought that this compound nucleus formalism, that everything goes through a resonance, it should be the more or less the width in the incoming channel times the width in the outgoing channel divided by the Lorentzian form with the sum of the two of all the widths. And what you said is somewhat different. Can you elaborate a bit?
Yeah, no, this is exactly what you are saying. Essentially, this is what...
yeah, exactly.
Yeah. Yeah, I mean, this looks like a Breit-Wigner. Essentially, you see the gamma here in the entrance channel, that in our case should be like a carbon-carbon. It is replaced by the transfer amplitude because you are measuring nitrogen on carbon. You're measuring a transfer reaction, okay? And this is something that you can measure. I mean, you can easily measure from experiment. This is something that you can get from experiment. And then this is exactly the gamma in the output channel. So it's like you are doing a two-body reaction, essentially. And this gamma is really the gamma of the resonance, the total gamma.
Ah, it's a total.
Yes.
Okay. Thank you.
One last question by Carlos.
The problem with the reaction theory is really a big one. We have 80 years of nuclear physics and books written by so many fantastic people, but we are always doing very simple things.
Yes.
And we are always using probability concepts. For example, I see carbon-13 alpha N, okay? So you must carry an alpha within another nucleus and you make a transfer. So how do a theorist like Stefan or Akram does it? So you have distorted waves for initial and final channels with final state interactions and so on. But you have to care by the wave functions because transfer is matching of wave functions. So you have to take an overlap. And then these are all, you see, these are all parts that we do separately. And then you say, well, but what is the probability of the alpha particle being inside of the nucleus? You have to find a performation factor. Then you ask Gaute. Yeah, right. Yeah, but yeah, the question is no question at all. I mean, is I'm just thinking that you are talking about dynamical reactions, and in the end, we are not really doing it. We are doing a lot of, you see, you pick up here a structure, you pick up here reactions, and you know, and we have been doing this for 80 years, right? So many of the things can go wrong with this.
Yeah, but then
that's what you can do.
I agree because you have,
I think
you have to be very
these guys in
careful.
nuclear structure, or these guys in effective field theory, they think life is simple. You just sit down and calculate Feynman diagrams and so on. But try to do this.
But then you run an experiment. You don't have to forget that we go through an experiment. And what you are saying, it may influence the absolute value. But since you are not, I mean, you are just ending up with something with a, let's say, a trend, an energy trend, and you get the absolute value from direct measurements. Somehow you are on a safe side. And yeah, I mean, we run this transfer experiment, but then from all the data, we just select part of it, okay? So we just select a portion of it. So you know the story of the momentum distribution. I didn't tell a lot of details coming from the data analysis because we go through this momentum distribution analysis. We just select a portion of it in order to stay in the quasi-free region, and somehow we are confident that what we are obtaining within experimental errors is, let's say, can be good.
Okay. I think this makes a great topic for the discussion, as well as the factorization in your formulas. I think that's another question we should discuss. But for now, I think we should
thank you
stop,
so much.
since you all want to have coffee. So let's thank Aurora again. Our next speaker is Renato Higa from the University of Sao Paulo.